gentlemen, I am Stephen Mercer. I'm a member of the LabVIEW R&D team. And today, I am going to tell you a little bit about why Dataflow works. Why is LabVIEW an important computing language in today's modern computing environment? What makes it so interesting to all of these engineering projects that you've been hearing about in the keynotes? Why is it a Dataflow language? Why does that appear to be such a nice paradigm to program in? And how can you take more advantage of that? Today's conversation is going to be a little bit more philosophical, perhaps, than some of the other sessions that you may have attended this year. Certainly more philosophical and more invigorating than ones I've given in the past. And I'm going to need help from the audience to make this work, so be prepared to play along, please. As promised, we'll begin with a potato. Can someone in the audience tell me why this potato is not falling down?
It's supported by a pillar.
It's supported by a pillar. Excellent. And why would the potato on the pillar not suddenly fly up in the air?
Gravity. Air pressure.
Gravity, air pressure. Wonderful. So now, why doesn't the potato fall? I have removed the pedestal.
We're in space.
We're in space.
It's just a picture.
Thank you! It is a picture of the potato. As promised, this is the potentially non-existent potato. Now, this potato was the inspiration for this presentation because one of my good friends, a friend of the family, she's the mother to my nephew, and she's cooking in the kitchen. And she has her laptop open to a recipe. And there's a picture of a potato on the screen. And my nephew looks at this and he says, why doesn't the potato fall down? Because when he takes a potato and drops it, it falls, but this one's clearly hanging in air. So I have to tell him, it's a picture. And if I wanted this potato to fall down, I'd have to write some code. I'd have to program some animation to make sure that it actually moves down the screen. And my nephew is a very bright young man, and he thinks about this for a minute, and he looks at the actual potato on the counter and he says, so where's the real world's computer? A reasonable question. We've gotten very good at digitizing data. We can take audio streams, we can turn them into MP3 files. We can take video, compress it down, transmit it across space so we see pictures of faraway worlds. We model all sorts of physical phenomena and computer simulations and flights and all sorts of things. All of space translated into zeros and ones. You could imagine it. Now we can't actually do this because there's this little problem of a computer that's part of the universe needs more RAM than the universe could store. But in theory, if we had a computer sitting outside the universe, it could simulate us. It could be running this. And every time we had an atomic clock pulse, and I use atomic in the real sense of the word as truly, physically indivisible atomic, a few things would move. A cork would shift position. A string might vibrate if we can prove those exist. All the little fine-grained changes would end up being some computation that ends up changing that string. And so this giant computer churning through the state machine of the universe, and let me tell you, that is a very large enum, is doing this gigantic computation over and over, and then rendering it on a very large 3D screen that we call reality. So we can take the universe and analogize it to a computer. But can we go the other direction? We model the universe as software. Can we use the universe as a model for the software instead? So that we can learn better how to program by looking at the physical phenomena around us. I believe that we can, and I believe that we can so long as some of you in this audience like candy. Woo! Now I am reliably told by the internet, which is a very reliable source, that the Snickers bar is the single most tasty, well-sold, highly desired candy bar in the entire world by orders of magnitude. Nothing the human race has produced is as tasty and as desirable as a Snickers bar. which gives me a high probability of success when I believe that there are people who like Snickers in this audience. Please nod your heads, or this is going to be a very painful conversation. Good. I need 2 members of the audience who like candy bars. Please come up on stage. You 2. Right here. This is a Snickers bar. I would like you to share it so that each of you may have part of it. Open it up.
Have you seen or not?
Well done. Now each of you take a bite, please. We'll wait a few seconds to see if they die. Did I put enough? No. All right. Yeah, this was an example of killing processes. No. Thank you, gentlemen. You may return to your seats. I need 2 more volunteers, again, who like candy bars. 1, back there. Come on up. This is another Snickers bar. I would like you to share this Snickers bar without breaking it. How can you both have some of the candy bar? Without breaking it first.
Switch back. You have to open it first.
You gotta have a bigger portion than that. She's gonna enjoy it for a little bit, and then I'll enjoy the rest.
Try the other end. Well done. They've invented time sharing. I need 2 more people from the audience. Thank you, ladies and gentlemen. 2 more. Come on. I know your names out there, some of you, and I fixed your cars, so you might want to volunteer. Come on up. Thank you. Now this one's a bit more tricky. I would like you to share this Snickers bar without taking turns and without breaking it first. Excellent. You may return to your chairs. And this is how engineers meet and get to know each other. So, we have just seen several methods of sharing a Snickers bar. Romantic in LabVIEW, it's right? Yeah. All right, so we talked about we could break it in half. We can time share, back and forth. We can have simultaneous access. And there's one more that I'm surprised nobody has thought about. Any suggestions from the audience? What's the 4th one? Some of you must like comic books, science fiction. Morphological integration. We'll simply slam both of you into the same body so you can eat with one mouth. Physical technology is still working on this one. It does occur occasionally in biology. In software, we've got this one mastered. We'll come back to it. So, that was eating. Consuming a process, modifying the data as you're working. Now let's just talk about, let's just read this. You 2 here in the front row. This is where it becomes the potentially dangerous part. I would like you to read aloud the back of that Snickers bar together. The ingredients list. Nice and loud. All right. And as they're doing this, I'd like you all to notice that they're holding their heads together and they're staring intently. You see the pose? This is very important to this reading together exercise. Well done. You may stop now. Now, I would like you and Kazi to read that at the same time without leaving your chairs. The ingredients list off the back of the Snickers bar. Aloud. At the same time, please. Oh, so you're saying it's not really possible? Yeah. You would need your own Snickers bar to read? Yep. Okay. Oh, look. It's like I put a plant in the audience, which I did not actually do. Yes, you could just read it from up there.
Except I can't because I'm not wearing glasses.
Oh, well, he's not wearing his glasses. Still, assuming an appropriate technological upgrade, he could do so. When we're reading, we have a few options. We could put the heads close together. We have one person read very aloud, and that's equivalent to the other person reading it because they get to hear the same information. We could wait for one to finish and do the whole time sharing back and forth. And as we pointed out, we could project it up on the screen and suddenly we can all read it. And suddenly we can have massive broadcasting, and now the whole multimedia experience is complete, right? Just a few problems that always come up when we're trying to read together. Who throws away the wrapper when it's done? Who's responsible for that candy bar? What if the other person is still reading it when you throw it away and they're not yet done? And you've got all these, we'll use the term mutexes, that you suddenly have to worry about. Honestly, it's just easier if everyone gets their own copy. He can read it, and Kazi can read it. Everyone's happier, and it's easier to eat. Much simpler than any of the other solutions, and we all get a full calorie count. In fact, I'd like you to think about the fact that absolutely all data sharing is an illusion. When we're reading this at the same time, even when you're holding your heads close together, those aren't the same photons going into your eyes. You each have your own information stream. Now, we're not having to duplicate the entire chocolate bar. That's expensive relative to simply duplicating photons. It's a much lower, earlier technology. But it works, and it works quite well for sharing data in certain situations. Has problems over longer distances. Requires line of sight, that sort of thing. Every form of data sharing, if you look at it close enough, and I will leave that as an exercise to the audience on your own time, has some data copy somewhere in order to enable it. You can't really have two processors running on the same actual information stream. We'll talk a bit more about that as we go along here. So now let's turn this thing towards Dataflow. Dataflow is a model of parallel programming. It allows us to specify our programs such that we say, this operation is dependent on these upstream operations. And when that data is available, I can now compute. Because the programmer supplies all of this information, we can have very intelligent compilers. And the compiler can look at this information and can make decisions about the best method of data sharing. Is this two operations that need their own copy? Or maybe these two operations are really good friends and don't mind bumping noses or being combined into the same body. We can change the lifetime, and the compiler makes all of these decisions for us. It can evaluate all of that because it has information. And in fact, if you look at Java compilers and C++ compilers and all of these other language compilers, a lot of their optimizations come from looking at their text and looking at the source code and trying to identify from the code all of the best data flow paths. Because once they know the data flow, they can make better choices about data copies. LabVIEW's kind of nice. You as programmers specify that for us. It saves my team a lot of work. We just look at your code and go, okay, we'll just compile that. Two readers. You've all written code something like this, where you've forked an array and taken it to two places, and probably about half the room has posted to the forum, how can I avoid making a data copy here? And some friendly person who knows a little bit more about the deep underpinnings of LabVIEW has said, oh, you don't have to worry about it. LabVIEW's not going to make a data copy. So we got a search windy array and another search windy array. Now, what order are these operations going to happen in? Rob? Yes. It is unspecified. Rob is the very, first intern at National Instruments. He's been on the team for who knows how long. You can see his face in pixels on the LabVIEW 1 screen. He doesn't have a clue what order these are going to operate in. The compiler is smarter than all of us at this point. But what it could do is it could decide to run one and then the other. If we're on a multiprocessor machine, it could decide to run both of them at the same time on the exact same block of data. But wait, you said that there's always data copy, or I said, right? Well, if you think about it, you have two processors. The individual elements are being copied into the local caches of those CPUs. They're not computing on the exact same register at the deep foundation levels of the hardware. There is memory copy happening, but it's just not the expensive memory copy of RAM. It's a deep copy, a lower level technology, if you will. With one reader and one writer, now we've got a little bit more of an interesting situation. The compiler looks at this and says, well, I can't really just leave it to chance and just let the lower level hardware handle it. I'm going to have to do one of two things. I'm either going to go ahead and decide to make a data copy here so that each of them can run, or I'm going to let the reader go first, and then I'll let the writer go first. Then I'll let the writer work on it. Which one is it going to pick? You and I don't have a clue. For any given compile situation, the compiler is taking into account way more information than we have from this little picture. I can tell you that if this is the entirety of your program, it'll do one and then the next. But if there's other aspects of your program, if there's more code upstream, who knows what it could do. The point is that it's doing all of that analysis and coming up with an optimal solution. A solution that is, assuming the LabVIEW team has done its job right, actually fairly close to provably optimal. Now, two writers. Here, we pretty clearly need to make a copy up front in order for those two operations to have any sort of meaning. So we'll take the expense, we'll duplicate in RAM, there we go, full data copy at the fork. But not always. What's LabVIEW going to do here? And I guess I should say, what are the things LabVIEW could potentially do here? Because I certainly don't know all the optimizations. I'm not on the compiler team itself. I occasionally go wandering through the source code like some mad lunatic going, "Ooh, that's pretty." But I don't work on that layer. So what are the things that might happen here? Anyone?
Copy data.
You could eliminate the loop. So yeah, you could. There's a data copy, but this is where we get that morphological integration. We'll just combine the two loops into a single thing, and now we're back to copying element by element. Again, we're back to that deeper, cheaper form of copy as opposed to duplicating the entire array. Does LabVIEW actually do this? I don't know. I know because I was curious enough to actually go look that in this particular simple case it won't actually bring them together. But that's not a big deal because it's pretty rare that you have two operations that are just inverted like that. But there are times when we do clever loop manipulations like this. The whole point of this part of the conversation is simply to highlight the compiler is making these decisions, and it can make these decisions because it can see the flow of the data, because it can see who needs this data next, and where is it coming from upstream. The compiler prevents you from bumping noses as you simultaneously eat in both ends of the chocolate, and from pulling the candy out of someone else's mouth while they're still chewing. Next time someone asks you why LabVIEW is a good language, that's what you can tell them. This is the non-technical version of LabVIEW optimizes data copies and puts in the necessary mutexes where necessary and tracks data lifetime. Boring, hard, technical, much more exciting with candy bars.
Amen.
Now, this is fun. You cannot write this in LabVIEW. And I know because I've actually spent many, many hours trying to do so. And I've spent many, many hours trying to help customers out of the pit they've dug for themselves when they've believed that they can do so. It is not possible with today's LabVIEW that you can do this. So the first node over there is one that's going to read from disk into some shared storage. Maybe it's a DVR, maybe it's a global variable, maybe it's an uninitialized shift register on some sub-VI somewhere. There's a lot of things you might pick. It's going to read it into some storage. And then in these next two, it's going to do a read-only operation. And I see this all the time. I'm going to read my DAC configuration up, and it's got this big, gigantic block of data, and then I've got two DAC processes, and they're both going to use that configuration data. And why is it making a data copy of my entire configuration file? Well, because LabVIEW can't see it. But you can do this sort of simultaneous read and write in C++ and Java, and C# and lots of other languages. And so what makes the LabVIEW environment different? Well, as we look over literally the never-ending quest to share data, I do not guarantee that this is anywhere near a complete list. Every time I post this, somebody comes up to me after the show and says, "Oh, we should add 3 more." And I've finally given up and just said more. All of these things are all ways of sharing data between two processes. And they all have this thing of, I'm going to take some data in, and then I'm going to give it back out under different conditions. And those conditions are what lead to this plethora of different tools that we have for sharing data. But none of them get to that holy grail of write it and then read it 1,000 times later. And the reason is that there's no way that the compiler can prove that the access from these independent VIs is not going to collide. Either every VI is going to get one copy, or we're going to have to wait for one VI to finish. And that means you're going to need to wire the air cluster such that these two operations serialize. There's nothing that you can specify that is going to get you around that. Now, we've got some things that we've talked about in R&D where we could have a write once constant as a formal declared system. And then from that point downstream, for the rest of your program, you would never be allowed to modify that value. And we've talked about all sorts of arcane and magical structures that we could add to LabVIEW in order to help this along. They're all pretty cumbersome. They all come with caveats about you can never change the value a second time, or you have to have heavy-handed mutexes if you ever do want to change the value, and all sorts of weirdness. And it all comes about from trying to fight the data flow. If you simply did the read and then wired the array to both of those sub-VIs and actually produced a wire, LabVIEW would figure it out. When you fight the data flow, the compiler gets dumb, and it has to fall back on its best strategy. So, data flow safe, this is the definition that I use. I posted it last year at NI Week. All data is usable by one and only one process at a time, with a clear handoff from one process to the next. If you're working in LabVIEW, the by value types, routing them where they need to go. Directed queues, so data going into a queue, in queue, gets handed off to the queue buffer in memory, is dequeued somewhere else. LabVIEW is very certain that there is a clean handoff there, and so it can make the same sorts of optimizations and cheats. Compare that to a notifier. Notifier, you put data in, there are many readers that are potential. And each one might read, and then there might be a second reader that comes along dynamically. So it has to make a copy. So whenever you're working, you kind of want to stick to the ones on the left. You're going to find more optimal memory, more optimal performance than the ones on the right. I'm not saying the ones on the right are bad ideas. The ones on the right have reasons why they use them. Otherwise, we wouldn't have them in the programming language. But they come at costs. And they certainly, as the compiler keeps getting smarter, those get better slower than the ones on the that are with the green check marks.
Quick question.
Yes.
What are you with action engines and functional globals? I hear those intermingled.
What was that?
With action engines and functional globals, where is the separation for you?
Action engines versus functional globals. A functional global is an action engine that has exactly two actions, get and set, where you're not actually taking advantage of leave the data inside and let it do the operations. If you read the data out, you're forcing a full copy because there's one left inside. But if you add additional action operations like do this for me, where I'm not pulling the data out of you, I'm simply passing a message in, then it becomes more of an action engine. Good question.
What about data value references?
Data value references, well, that's that last line down there. If you don't fork them and you just are using them serially, nice and good. As soon as you start forking them, then now you've got data contention back and forth, and if you're pulling the data out, then you're making copies of it. If you're not putting it back in. So again, you're back to either things are being forced to be serial, or you're making a copy out of the DVR. You don't get the advantage of two things at the same time without the copy. When I say safe but non-optimal, that just means you've got overhead because LabVIEW is checking to see is there another process in parallel. So even though it doesn't have to do anything, it still has to look up and go, is there? No, okay. So if you're going to work within the data flow, if you're going to stick to it, what do? Well, I've got 4 tips for you. First one is run wires when possible. Seriously, just stop fighting it. I have debugged so many programs where someone is just resisting. I realize that there are cases when you're running a wire all the way to the other side of your diagram, and sometimes that destination is 16,000 pixels away, and that's why we have create sub-VI. And I know that sometimes you don't like having so many terminals on your connector pane, and that's why we have bundle and unbundle. And I know that sometimes you change your data types and you don't want to have to update all of these places, and that's why we have LabVIEW classes where the data is private. We have tools for managing this, folks. Please run wires. You get nothing else out of this conversation except for candy bars are good and wires are good. Wires are like candy. There. Remember, VIs execute, data is passed. Whenever you're doing your architecture, whatever you're thinking about doing, I have found that this little piece of advice has helped a lot of customers to really figure out how to architect their system in ways that are a bit more consistent with not creating data copies and creating these depots that have to be maintained and shared and such back and forth. A VI is something that executes. If you start using a data value reference and you keep opening it up, doing some modification to it and sticking it back in the DVR, and you have lots of parallel code that is doing that all on that DVR, you're treating that block of data as if it's an executable thing. And you're treating it as if it's a live computing unit. Data is meant to be somewhat dead. It should be handed from one process to the next. VIs are designed as operations. This is not a hard and fast thing. There's plenty of reasons to deviate from this, but as a general rule, if you hold this thought in your mind, I find that I've been able to guide a lot more customers to making better architectural decisions. Announce instead of request. Again, not something that you have to do in all cases, but something that has generally been a better guide. When you have lots of asynchronous processes, and they're all going to be talking back and forth to each other, if you write it in terms of, I need X, would you tell me X, and I'll just stand here and wait until you tell me, you tend to end up in situations, and I'm not entirely able in this conversation to explain why you end up in those situations, but you tend to end up in situations where you're making a lot more data copies and you've got a lot more time dependencies. Certainly you can see that there's that serialization that suddenly occurs. On the other hand, if you make announcements, so I'm doing my thing over here and somebody over there yells X, and then I go, oh, okay, well now I can go off and do something. I tend to end up with a system that is much more fluid, much more responsive, much fewer hang-ups on the same block of data. And then number four. I need 6 people who like Snickers bars. 1, 2, 3, 4, James, 5, 6. If you would line up on this line, just facing the audience, put your toes on the line, all the way across. All right. This is my assembly line inspection system. These are different processes. Snickers wants its logo to be correct. They are very paranoid that the printing is correct. So I'm going to hand you a Snickers as the producer of these. You are going to inspect them and make sure that the logo looks like the master copy. You're going to look at each one, you're going to say, yep, that matches. And if it doesn't match, you're going to hurl it into the audience, gently. If it does match, you pass it to the next inspector. The next inspector is going to do exactly the same thing. We're going to have a six-layer validation. Each one of you is going to check it and either pass it on or hurl it into the audience. Hopefully all the bad ones are rejected here at Jeff, which is why I picked someone with a good arm. And when they get down to you, just set them on the ground. They'll be packaged up later. As soon as I hand you the last Snickers and you've accepted it, sit down. As soon as you get the last Snickers and you've accepted it, sit down, and so on. So as soon as we're done, we're going to basically, the system will bring itself to a stop, right? All right, here we go.
What the hell, reject.
Capricious inspector.
Keep past that before you. There you go. How did you know that that was the last Snickers? I didn't tell you that was the last Snickers. I got more Snickers. Back to your seats. I'm dismissing the entire inspection team. Here. Oh, wait. What did you say? There were none left in my hands? So you looked ahead at the queue and saw that the queue was empty and decided that you were done.
Something like that.
I see. Yeah. Embed the stop signal in your communications channel. Trying to do things where the stop signal is communicated through some other mechanism, especially by somebody trying to do a preview on the empty queue and then trying to guess, it leads to problems. If you simply embed within your transmission signal, this is my data, so more to come, that's it. You're going to be able to write things that are much more pipelined, and you're going to avoid these weird off-the-books checks. And you'll end up with much fewer situations where you end up with these race conditions where LabVIEW's got, okay, I'm apparently done and I'll drop. And every once in a while there's this race condition against things because there was something that wasn't actually part of the data stream. But really, wires are good. Are there any questions? Well then, thank you, ladies and gentlemen, and I will now embed my stop signal in the communications channel.